Hi, which one of these has more information? ABCD or AAAA? Now, they're both 4 letters long, but it feels like ABCD has more information. Another example, take this first image and this second one, and which one has more information to you? Again, it feels like the second one has much more information than the first one. And the fact that we can intuitively feel like ABCD has more information than 4A's, or that the second picture has more information than the first one, the fact that we can compare that or feel that suggests that we can measure or quantify information. And that is where information theory comes in. Information theory is defined as everything related to quantifying, storing, and communicating information. So what is information really? Is it sounds? Is it words? Is it numbers? Well, kind of. That's just a form that it takes. But at its core, information is anything that reduces uncertainty. It is what gets you to go from not knowing to knowing. If I tell you something you already expected or knew, it's not really informative. But if I tell you something that's surprising, that's quite informative to you. Let's go back to these two images. The first one is very quick to describe. I can just say it's all blue and that's it. You got all the information. It was very easy to get you from not knowing to knowing. But the second one, that's a bit more complicated. I'd have to describe every shape, every color, every shade, every pixel even. Way harder to describe because it contains more possibilities, more uncertainty, and hence more information. And in fact, we can measure this information in little units called bits. We'll get back to that later. Now, you might be wondering, how exactly do we measure information? It's not exactly concrete or straightforward. And that is valid, to which I answer, how do you get information? What do you do when you want to know something or when you want to get information from a source? You ask questions. With each question, you get more bits of information, getting closer and closer to the final answer or the message. The more uncertainty there is or the more information there is to get, the more questions you need to ask. So a way for us to measure how much information there is for us to measure how many questions we need to get the answer. So the amount of information can be measured as the number of yes or no questions you would need to ask to get the message. Why yes or no questions? Because they're the simplest kind. Computers work with zeros and ones. So measuring information in yes or no questions is easy to implement digitally. I said previously that we use bits to measure information. Well, bits are simply the answer to the yes or no questions. A bit can either be a 0 or a 1. That's what a bit is. 0 is no, and 1 is yes. Recap. So far we learned 3 things. 1. Not all messages contain the same amount of information. As we've seen, ABCD has more information than AAAA, and some images have more information than other images. 2. Information can be thought of as how hard it is to go from not knowing to knowing. 3. We can measure information by how many yes or no questions we need. Alright, let's try this out. I'm thinking of a letter between A and H. That's 8 possibilities. How much information is in that? Or, let me rephrase, how many yes or no questions do you need to figure out the letter I'm thinking about? Let's play this through. You can start off by asking if the letter is in the first half. I answer yes. You eliminate the other half. So now we've narrowed it down to A, B, C, D. 4 possibilities left. Again, you ask if the letter is in the first half. I answer no. We eliminate A and B. So now we're down to just C and D. Pretty straightforward. You ask if it's C. I say yes. And bingo. You got it in 3 yes or no questions. So that means the amount of information in that answer is 3 bits. And this sequence of questions works no matter what the letter was. Each question splits the possibilities into 2, and to go from 8 possibilities to only 1, you need 3 splits, hence 3 questions, hence 3 bits. Now, you might not have thought of this sequence of questions. Another way would be to go one by one, asking, is it A? Is it B? Is it C? You might get lucky and get it in one question, or you might get unlucky and need to ask 7 questions. Or, even worse, you could ask redundant or inefficient questions. This leads to more questions asked than needed. This is why we talk about entropy when we're talking about measuring information. Entropy is the minimum average number of yes or no questions you need to ask to figure something out. I know, that's a mouthful. It's the best case average. Let's see this in action. How much information is in a number between 0 and 15, 15 included? How many bits would I need to store that number? Well, there are 16 possible values. Take this number for example, 1011, or yes, no, yes, yes. And each bit / answer is associated to a value. Starting from the right, we begin with 2 to the power of 0, which is 1, and the next one is multiplied by 2, and the next is multiplied again by 2. You get the gist of it. So we've got 1, 2, 4, 8. Starting with the first bit on the left, we are basically answering the question, is the number bigger or equals to 8? Since it's a 1, the answer is yes. And just like the alphabet example, we eliminate half of the possibilities. Next, we are asking, is the number bigger or equals to 8 plus 4? Because we said yes to 8 previously, that's why the 8 remains. Hence, is it bigger or equals to 12? The answer is no, so we eliminate the numbers 12 to 15. Next, we're asking, is the number bigger or equals to 8 plus 2? The answer is yes, because it's a 1, and we eliminate 8 and 9. Finally, we're asking, is the number bigger or equals to 8 plus 2 plus 1, which is equals to 11? The answer is yes. We eliminate 10 and are left with 11. So it takes 4 bits to represent a number between 0 and 15, 15 included. The entropy is 4 bits. For those of you who recognize this, or those who don't, this is a different view on binary representation, the way computers store numbers. Any number can be represented with a sequence of bits. Each bit is associated to the power of 2, with the powers incremented, and if it's a 1, we add that to the sum. If it's a 0, we do not add that. Yes, but how do we calculate this in a quicker way? For this, we need to introduce something called base 2 logarithm. It's a function. You give it a value, it spits out another. Or, and I've got 2 ways I like to think about it. The first one is, it's the answer to the question 2 to the power of what gives me x, or how many times can I divide x by 2 to get 1. For example, you give it 8. 2 to the power of what gives me 8? Well, 3, because 2 times 2 times 2 is 8. Or, how many times can I divide 8 by 2 to get 1? Well, you divide it once, you get 4, you divide it twice, you get 2, and you divide one more time, and that's 3. The same number of questions you needed to figure out the letter I was thinking about between A and H, 8 possibilities. And you guessed it, you can generalize this to log base anything. The anything here we'll call n. It's the answer to n to the power of what gives me x. And here we have a few examples to show a function in action. When you ask questions to figure something out between a bunch of equally likely possibilities, each question narrows the number of possibilities down by half. Hence why the logarithm base 2 function is useful. It tells you how many times you can divide something by 2 until you reach 1, of course. So, if there are 2 outcomes, log base 2 of 2 is 1. If there are 4 outcomes, log of 4 is 2. If there are 8 outcomes, that's 3. If there are 16 outcomes, it's 4 questions. So when you have equally likely outcomes, log base 2 of the total number of outcomes gives you how many questions you need to ask to find out which outcome is the answer. And the number of questions you need to ask is the amount of information, so it just gives you the amount of information in bits directly. But in those cases, each outcome was equally likely. What if they're not? If you have one outcome that's much more likely than the others, well, you'd start off there. You'd start off by asking questions that confirm or deny the most likely outcome and only get to the rare outcomes at the end. This way, you're much more likely to figure it out in the least number of questions possible. Because you're asking fewer questions to get the most common outcomes, and you're asking more questions only when it comes to the rare outcomes. So you'll be often asking a few number of questions, and you'll rarely be asking a lot of questions. Therefore, if a specific outcome is expected or more likely, then the message carries less information. Therefore, if something is expected, then it carries less information because we're asking less questions for that one. But if an outcome is very unexpected, then it carries more information because we ask a lot of questions to get the rare outcome. Let's go back to the example from earlier with the 8 letters. But this time, well, you know that I'm a big fan of the letter A. I think of the letter A half of the time. The other letters I don't really care about, they're equally likely. In that case, it's like having 4 A's over 8 outcomes, with the other letters only appearing once. You are figuring out the other letters out of 8 outcomes, but you're trying to figure out A out of how many outcomes? Well, if we split the letters into 4 groups of 2, with each group having a single A, then it is like trying to find A out of 2 equally likely outcomes. A and X. X can be whatever here. 2 equally likely outcomes. Log base 2 of 2, that's 1. So the outcome being A only had 1 bit of information into it. You only need 1 question for it. So it's like we're choosing A out of 2 equally likely outcomes. So we divided the total number of outcomes by the number of occurrences of a certain outcome. Well, that is just the inverse of the probability of that letter. And to get the amount of information in that outcome, or how many bits of information it contains, we just plugged it into the log base 2 function. Equals to log base 2 of 1 over the probability of x, which is equals to minus log base 2 of the probability of x. That is just a property of the logarithm. Log of 1 over x is just equals to minus log of x. So, okay, sometimes we only need to ask 1 question, sometimes we need to ask more. But on average, how many questions would we need to ask? We would need to ask only 1 question about half of the time, since that's how often the letter A appears. We would need to ask 3 questions about 1/8 of the time, because that is how often the letter B appears. And we repeat this for the other letters summing up, which gives us 2 as a result. Meaning that on average we'd need to ask 2 questions to find out, which means 2 bits of information, because entropy is the minimum average number of questions we need to ask. This is in contrast to the unbiased example, where we would always need 3 questions, which proves our point earlier. If something is biased, we have expectations, and hence there's less information in it. Now, we calculated that the minimum average number of yes or no questions we'd need to ask in this situation is 2. So the entropy is 2 bits. Now, of course, we can generalize these calculations into a formula that gives us the entropy in a message, or how much information there is. Here is the formula in all of its glory. The entropy of x is equals to minus the sum over all possible values of x, the probability of a specific outcome, multiplied by log base 2 of the probability of that specific outcome. X is the thing we want to describe, the message. H of x is the entropy of x, or the minimum average number of yes and no questions needed to describe x. The weird symbol you see is the sum over all possible outcomes of big X, and the specific outcome, we symbolize it with little x. P of little x is the probability of that specific outcome. And of course, log is the logarithm base 2. Now, minus the probability of little x multiplied by the log base 2 of the probability of x gives you the information content of little x weighted by its probability, by how often it appears. I hope that made sense. I really hope you got the intuition behind that formula. Often I find, personally, that this formula is given way too soon. That's what I thought when I was first presented with the formula. It's been a ton of fun working on this video. I'll put a link in the description to the code I wrote for all of the animations you've seen in this video. I've used Manim, the software developed by 3Blue1Brown. Big thanks to him for actually making it free for everyone to use. I can't believe I'm saying this. If you like this, drop a like, subscribe. Oh god. Bye!